Okay, good. I should be recording now. Okay, so I'm assuming everybody is here. If you know somebody is still coming, I can wait a few more minutes. Okay, no, I will start then. So the topic of today's lecture is about state value evaluation. So we will not try to find the optimal policy, but we will just have the policy and we'll want to evaluate its value in the model-free case. So up until now, we always knew everything about the model. Then we knew the model, but we didn't know the state. Now we will see that we will know absolutely nothing about the model. The lecture will be divided in two, roughly speaking. Of course, the times are a bit random as usual. The first half will be about the first basic methods. So essentially Monte Carlo, and then we will use the basic definition of value. We will define the Monte Carlo method, and we will see how it works. Then we will switch to learning rates. We will see what we mean by that. Then we will do the temporal difference, and we will try to mix Monte Carlo and temporal difference. And after the break, we will do something which is a bit more convoluted from a mathematical part, but it's actually very simple. We will see to implement. So we will do temporal difference lambda, and we will generally speak about the eligibility traces, which are a quite common and useful tool we will show it will help us to retain some sort of short-term memory of past experience when we do the update. Okay, so as you've seen, I decided to share a notebook, which is an incomplete notebook, so you can follow on your own. I left some part blanks, and then I think that you can decide whether I can give you very short period of times, and you can think about how to fill those blanks, and then I can give you the solution, or we can just skip it and I will provide the solution. In any case, after the lecture, everything will be available to you. Okay, so let's start. Okay, so as I said, the topic now is how to evaluate the value function. And so we are dealing with a task in which we have a policy, but we have no idea of the underlying model of the environment in which we live. But we can, of course, have some access to it. We have access to it in the form of the experience. So we have we can produce trajectories, which are just the set of consecutive state, action, and reward as the environment. So the state is exactly the state I'm in. I do an action following my policy. I get a reward, a new state, and I follow it until termination. And I can do how many trajectory I want. And this is the only information I have on the model. But we can see that just having this information, we can evaluate the value. Indeed, the value function of a policy, so the value function of a state given a policy, has a proper definition, which is just the expected return when I start in that state and I follow the policy from that point onwards. So this is the first definition of the value v given a policy pi of the state x. It's the expected sum from all consecutive times of a discounted reward, so gamma to t reward t, if I start exactly in that at time 0 in that position S. And this expectation pi, it means that all the action has to be taken with a probability given my policy. And we will see that this is already enough to have our first class of algorithms, and this which will be called Monte Carlo evaluation. The second part we deal with temporal difference will exploit the fact that we also have a recursive property of a value function, which says something different, and you have seen it in the lecture 2 lectures ago with Professor Celani, which is the value, the expected value of the sum of the immediate reward plus the discounted value of a successive in the successive state. Again, if you start in the right state and you follow the policy. So you see that the first definition is just needs the returns. If you know the returns, you can calculate it. The second one, you need to know the value in the next state to measure it. So there will be two different ways to deal with the two definitions. Okay, we want to try the methods I'm going to describe and that you've seen in the theory class on an extremely simple model, and this model is just a random walk. What we mean by a random walk model, we mean that the environment is just a string of states. Now here they are called A, B, C, D, E. We will call with numbers starting from 0, 0, 1, 2, 3, 4. And you can have in every state you have two actions, just go left and go right. And these actions do what they say. So if you take action left, you always go left. If you take action right, you always go right. There are no rewards at all, except for when you are in the last state and you do a right action, you get a reward of 1. And if you end up either in this square here or in this square here, the episode terminates. So these are terminal states of a random walk. Okay, this is the environment. We want to do a random walk, which means that we are taking a special policy. Of course, if we want to study the random walk, what policy should we take? So, small question for you all, just to start you off. What is the random walk? The basic random walk. I can choose one of you and ask it, but maybe you can just.
Is it 1/2?
Perfect. Yes, it's 1/2, 1/2. Okay, good. So it's just, this is the policy which says, okay, I have 1/2, 1/2. I can go left, go right. I have no bias. Good. So we will try to evaluate the policy of going half the time left, half the time right everywhere. So the policy is the same in every state. And I want to know the value of each point. And we will use algorithms to do that. But of course, this is a very simple problem. We could also know what is the optimal value before doing any simulation, because we can actually calculate the optimal value. And this is, I wanted to ask you this, but we can skip it. It's very simple actually. That the fact is that for each point you have, if you remember the Bellman equation, your value is, now we can write 0.5 here and 0.5 here. So what is it? Essentially the value in a state is half of the value from left, half the value from right, because the reward is always 0 except from the last part. So in all intermediate states, the value is the mean average of the two values left and right, except from the last place in which you have the mean average between 1, which is going right, and the value of the left part. So essentially, it's very simple. This means that since you're doing always the mean value of left and right, mean value of left and right, this means that this is a linear function which goes from 0 to 1 from the path. So the optimal value we can write in this case here, for example, it's going to be 1/6, then 2/6, 3/6, 4/6, and 5/6. Okay, this is the optimal value. So essentially, all we are going to do today is just to find these very simple numbers which we already know for a very stupid system. But the way we will find them again is going to be the interesting part. So from the point of view of a simulation, I just defined this class here, which is the class of the environment. I've defined it much more complicated than it needed to be, because actually this is a way in which environments are generally structured also in libraries online. So if you go to OpenIE libraries for environment, generally speaking, the idea of a structure in which they are written is the same. So I wanted you to have something to compare. Okay, it's not exactly the same, but it has the same structure. So generally speaking, it has an initializer in which you just define what is the observable space. In this case, it's very simple. We have just n states. I'm not considering the terminal states. And the space is just literally the array of 0, 1, 2, 3, 4, 5 up to the size. The action space we have to define is just -1 and 1, left and right. And we just decide that we start in the beginning, in the middle. This is that it's not important. We will always find in this kind of libraries with real environment, we will also find a reset function which just brings everything back to the start. And then we will always find a step function which takes just the action. So in this case, it will take just -1 and 1. We'll create the new state, we'll create the new reward, and we'll give the new state, the reward, and a flag which says, I've reached termination of the episode or I didn't. In this case, it's very simple. The current state will be incremented by the action, so it will either -1 or 1. And then I will just check whether the done condition is satisfied. In our case, you remember the condition was if you go to here, so if you go to -1 or if you go to n plus 1, okay? And this is what it's written here. So if you either you go to -1 or you go to +1. And if you go to +1, the reward is going to be 1, and you're done. If you go to -1, the reward is 0, and you're done. And in all other cases, the reward is 0, and you are not done. So the flag is false. Okay, just to point out that generally speaking, all these libraries online, you will find a render, which just helps. When you use this function, it will pop up some picture of the state of a system. I didn't put it here because it was simple, but just this is the way a general environment is created in most of the libraries you can find online. Okay, let's try it out. So I just create this random walk environment, and I'm doing 5 episodes. I start saying, okay, I'm checking whether the episode is finished, and I just take the current state. I take an action randomly with this policy. I'm giving the action to the step function, so I will get the new state, the new reward, and whether the episode is done or not, and I'm just printing it. Okay, this is just to check if everything is working. And this are the typical episode. So this is an entire episode. You see, it's not done, not done, not done until it's done. And I have the state. I have the action which I took, which was -1. Indeed, my new state is 1 because I was 2 minus 1, 1, and I got no reward. And I got no reward. And then you see it ends because the the final state is -1, so it has left on the left. This means that it's done, it's 0 reward. Okay. This is all the information our different algorithms will have access to. So instead of having, like we did with dynamic programming, which you have the proper probabilities, the function of the reward, the transition, no, this is all you have to evaluate the value function. We will have to create algorithms which take this list of numbers and create the evaluation of the value function. Okay, the first algorithm, so as always, if you have questions, please ask at any point. Okay, the first algorithm is the estimation by Monte Carlo, which does basically what it's written here in this section. I see Mike. Okay, essentially, we want to collect the values of this return, and we want to average them out. This is what this definition is. So the idea is that the agent interacts with the environment and produces many trajectories. From the trajectory, I can calculate the returns at each time. So if I get a trajectory from T0 to the termination, I just sum over all the discounted reward, and this is my return for that time there. And then I I link the return of that time with the state at that time. Okay, so for each state I have all the returns which have really started in that state there. This is going to be called the first visit Monte Carlo method, because since I want all the in this average, I want all terms to be completely independent. In one trajectory, I will take only the first time I visit the state. I will calculate the return for the first time, and I will only keep that one. So for each trajectory, the first time I found a state, I'm calculating the return from that point onwards, and I will associate the state with that return. Okay. Then I will have to keep in memory all the returns which I linked to that state, and the values are nothing more than just the average of that. So the value will be the average of all the returns I've experienced starting from that state. Okay, the pseudocode is practically the same as the code. I want a policy to be evaluated, which is my half left and right. I initialize the values arbitrarily. I will just initialize them to 0. I will have a list of returns which are basically 0, which means I have not visited anything yet. And then for each episode, I'm gonna start from the beginning. I'm gonna sweep up to the end, and then I will calculate the returns for each time step. And then if it's the first time I've seen that state, I will just say, okay, let's append to that list of that state the return I've just saw. Okay, have you a question about this? Okay. This is just a very helpful tool which computes the discounted sum. So this is just a function which does, it was written magic for computing discounted even when I found it. It just,
sorry.
Yes.
Please, can you re-explain the last step of the algorithm?
Okay, sure. So we want to evaluate this function here, right? We want to do this formula, which is the expected value. So in a sense, the average value of all the sum from one moment onwards of the discounted reward, if you start from a state. So what you do here in this pseudocode is you calculate the which means the sum of all the future discounted reward from that point onwards, and you calculate for each point of your trajectory. And then if you are in a state ST, which you have not seen before, so it did not appear in the state before, you take that value of return, which is the sum of, from that point, gamma reward, first reward, gamma second reward, gamma squared, third reward, etc., etc. You take that reward and you store in a list which is connected to that state. For example, I do the first trajectory and I calculate that the state 0, I found it, and the return from that was 3. Then I do another trajectory and the state 0, I found a reward of 5. So I will keep in a memory 3, 5. I do another trajectory and I never find the state 0. Okay, I do another trajectory and I found again 5. And then at the end, I will have in memory associated to the state 0 a list of values which are the different returns which I found in the different trajectories. 3, 5, 5, then 6, 1. And then I know that the value is just the average of those values, or those numbers I found. Is it more clear?
Yes, thank you.
Perfect. Thank you for the question. Okay, so exactly as said, this is the pseudocode. Now we're going to the code. Again, we define a class, which is just our algorithm, and it just needs to know what is the system size, what is the gamma we want to use for the discount. And now I'm just doing a list of empty arrays, and I want one empty array for each state. So I want this list, which if I have size equals 5, I will have 5, 0 array. Then the update at the end of a trajectory, I will require from the user, I will require what is the trajectory of the states and what is the trajectory of the rewards. And then what is my my single episode update? I will just say, okay, at the beginning of the episode, for sure you have not visited any state yet because you have not done anything. Then you calculate the returns. And this is a function which returns the for all time step the cumulative sum afterwards. So it's truly the now we have an array with all the returns. So we have G0, G1, G2, G3, G4, etc., etc. And then we just have to do the last part of the algorithm, which is for all the time step. So this is the time step. S will be the visited state. And then we just want to do what? We just want to append to the list of the returns of that state that return if we have not visited that state. Okay. So I will leave you like 40 seconds. You don't need to write it because I will give you, but I want you to think of what here the code should be, okay? And if you have no idea, then you can ask me, and you will see that maybe this will be helpful for you to have a mnemonic idea of what we are doing. Okay. Have you thought what goes? Are you completely lost? If you're completely lost, it's good in the sense that you can ask questions. Otherwise, I can show you the solution. I go on, right? I mean, those few with come on, please note sometime. Okay, what I said, what you need to do is, if you've not seen the state yet, you should store in memory the return connected to that step. This is exactly what goes here. If the state S was not in the visited list, then for that state S, you should append, so add to the list, the return coming from that step, because this is exactly what is sum from 0 to infinity gamma reward, okay? I'm just storing a new one. I found a new times, I started a new one. And then I was just saying, okay, you know what? I have visited this state. So the visited list now contains also the new state. If the visited, if the length of the visited list is the same as my size, I do not need to go further because I know that I saw everything. Okay, this is Monte Carlo first visit. Every time you see a new state, you store the return. And then it's very simple. I just need to estimate the value. I have the store of all the returns I saw. I do the average value, and this is my number. I go. Okay? Perfect. So there are two problems with this algorithm. The first problem is that it needs to reach the end of an episode to make a guess. So if you cannot do it at half an episode, you need end of an episode, which can be very costly. The second thing is that it needs to store in memory all the returns. So you can imagine that here we can, but if you have a system which you have to start to store like millions of numbers, it gets really uncomfortable. So for this case, we go into the learning rate. Essentially, instead of storing the returns and then you do the average of returns, you do this, which is like a stochastic way to do that. So I do the same thing, basically, but then instead of just storing the return, I do an update. An update, it means that whenever I find the state, I say, okay, my last approximation of the value was V, and now I will add a small quantity alpha multiplied by the return which I found minus the value. So since the return is what I expect in the end to average out as the value, this G minus V goes in direction which at the end should bring me to the good part. Okay, so I will do an update now. I do not need to store. Whenever I got a return, I will just say, okay, the new value is the value plus a small difference between the between the return I got and the value. Okay, and you can see that if alpha was 1, it means that basically every time your value is assigned to the return I've just saw. It's like, okay, I will forget my past. This is my new return. This is my new value. If alpha is smaller than 1, it mixes up all the returns I found so far. Okay, and as before, I have a small code, which is again very simple because it's as before. Now I don't even care about visiting it because the first visiting was about independent trials. Now I'm mixing everything up. So what I have to do is just have to calculate the return, which are calculated here. And for all the steps, all the states, I just need to update my value with this small quantity alpha, the return minus the value. Okay, so you can think a second about that. It's even simpler than before. Because for all the times, for all the steps, the only thing you need to do is sum this alpha, which I apologize, now it's called learning rate of the value, which is a very standard name in the library, multiplied by the return, which is G, the return I found at that step in that state, minus the previously old value for that state. Okay, so the value for that particular state which I visited, it's in that time step, it's equal to the return for that time step minus the value which I previously thought it was the right value. Okay, good. Now let's estimate how this works. And this will be something which I will do with different algorithms. It's very simple. I will do 100 episodes. I will, now we can put the random policy, which was that of a random walk. I'm putting gamma equal 1, just for simplicity. So there is no discounted reward. So we know that the optimal value is 1/5, 2/5, 3/5, 4/5, and 6/5. I'm taking a random alpha, which is small, 0.05. The optimal value, we have said that now we know what they were, what they are. 1/6 to 6, 3, 6, 4, 6, 6. And I will create an environment. And I will try to do both of the, I will create both of the algorithm. And I want to evaluate how different the values measured by the algorithm are if I do n episodes of learning, and I will average out between many different starts. Okay, so this is for each algorithm will have a number of episodes. And I will have to store the trajectories for each episode. I will reset the environment. I will do the episode as before. You see, the action is the random action between left and right, and I will get a new state, a new reward, and I will essentially retain in memory the trajectory for the state and the trajectory for the reward. And then I will say to the Monte Carlo, the two algorithms, so the Monte Carlo with the first visit and Monte Carlo with learning rate, I will give them the two trajectories, and I will say, okay, give me an evaluated of the values. And then, since I know what are the values in the optimal, what are the optimal values, what are the real values, I will just check what is the error between what I got at a certain number of episodes of learning and what is the real one. Okay. I apologize. I have to define this. Yes. As always, I forget to. Okay, it will take a bit because I asked him to do a large number of trajectories. Okay, so this is a typical efficiency curve. You can see that the first visit Monte Carlo, it's rather robust. It goes to 0 quite well. This is the error. So the error, this is the error for all the episodes. So after 100 episodes, the average error for the first visit Monte Carlo is rather small. And you can see that the Monte Carlo, with a constant learning rate, actually learns quite well and then fluctuates around a bit. And this is the reason why you know that the learning rate actually should go down, and there are the condition for the learning rate in time to be sure that the algorithm converge with probability 1. And we are not using that. We are using a custom algorithm which is known to have this problem. It will go fast toward the solution, then it fluctuates. Okay, and you can clearly see that, for example, if I have a much larger learning rate, then I will have even worse performance, okay? But if I have a very, so this is because I'm trying to change my value much faster. So the beginning I learned very fast because I was very far from the right solution, but then it's a mess. And if I do a very, very, very small learning rate, of course, this will, in the end, will be a much better solution, but it takes a very long time. Okay, so we've done the first very simple thing, which was Monte Carlo. We had a way to define the solution as an average, and we exploit that average. We have not used the Markovianity. We have not used the recursive property of the value function. We have not used anything. Now we will do exactly that. So now we will use the property that the value can be explained as, can be given as the instantaneous return plus the discounted value of the next state. Okay, and as you've seen, you can define this, what is called the temporal difference error, or TD delta, which is the reward plus gamma, the value in the next state, minus the values in this state here. And you can see that it's defined, it's taken as above. Above you have the value, reward plus gamma, the value in the next state. And here the delta is defined exactly as the reward plus gamma value in the next state minus the values in this state. Okay. And the meaning, the reason for that is very simple, which is this delta here should go to 0, because exactly as the value is the expected average of return plus gamma value, if you do return plus gamma value minus value, the expectancy is to get 0. And the meaning of delta is actually very simple to understand, because the meaning of delta is the reward plus gamma value, which is okay, let's do it another way. It's the reward I got, which is the real return, which the real reward which I experience now. So the reward I got now, and the other thing is the reward which this V minus gamma V. Let's do it in the other way. Okay, I apologize. 1 second. Let's do it. Here. Okay, so RDT is the reward I just got, and the value minus gamma, the value in the next state, is the expected reward which I should have got. Because this is clearly, since one is the value at time t, and the other is gamma value of time plus 1, this is the expected reward I should have got now, and this is what I really got now. So delta is basically the difference between what I truly experienced as the reward and what is the expected reward which I should have gotten at the time t. Okay, this is what it means in words instead of a mathematical sense. Again, so the pseudocode, so what is the truly nice thing about this? That this does not require a whole episode, because the definition of delta requires only the state at time t, the reward, the action, no, the action does not, but you have to do an action, you have to get a new reward, you have to get a new state. So if you do one single step, you already can evaluate delta, and then you can do this update. Okay, so Monte Carlo requires the whole trajectory of the whole episode to do one single update, and temporal difference requires only one step. And this is indeed the pseudocode. Again, you have a policy to be evaluated. You have this step size alpha constant very small. You start with the value which are randomly, but the value for the terminal states at 0. And then essentially, whenever you do whatever episode you're doing, whenever you're doing an action from a state S, you can calculate this delta, which is the reward you really took, plus gamma, the value you think it is the new state, minus the value you think it is in that state there. This is delta. And you update the value by a small quantity by this difference here, which is the difference between what you experienced, R, and what you expected, gamma V minus V. Okay? And you do it over and over. Every step you can do this update. Again, I'm a bit late, but then you can see that again I created an algorithm class, which is very simple, and we have a very simple step update. Now, no, it's not a single episode update. You do not require the whole trajectory. You just require very simply a state, the reward, and the new state. Okay, and okay, you can again spend a few seconds to think what is the update to write here, and it's just this line here. Okay, so I will give you 2 seconds. The only thing which needs to be a bit dealt with care is the fact that if the episode is done, then I do not have the new value, because the value of all the terminal states is 0. But that is the only thing that has to be taken with care. So each state, I will calculate the value in the new state, or I will put 0 if episode is finished. I will do reward plus gamma value in the new state minus the value in the state in which I'm in, and I will update the value. And this is exactly what is done here. If I am done, so the episode is finished, the delta is equal to reward plus 0, because I'm in a terminal state, minus the value I have in that state. If I'm not done, the delta is the reward plus gamma multiplied by value in the new state minus the value in the state I'm in. Then I do just the small update. The value is, I just sum this small alpha, the small coefficient, which is now is a learning rate, sorry, and I will multiply by delta. So this entire temporal difference algorithm is actually essentially 4 lines, and it's very, very simple to write. Okay. The whole idea of today is that all these things are very simple to implement in the most basic sense. Again, I just wanted to let me copy this because I will need it, otherwise I apologize. Okay. Here is the evaluation, sure. Okay, here what I do is the same as before. So I do 50 runs of averaging, and I do 100 episodes. And now I compare the results I get with this temporal difference 0, which you just take every step. You see now, instead of waiting for the end of the episode, at each step, I'm saying, okay, I have a new state, new S, I have the old state S, I have a new reward R. I can ask to the method of temporal difference 0 to do a new update of the value. Okay, Before, the update was after the whole episode. Now the update is in between single steps of the episode. Okay, and you can see now essentially what happens for the system, and it's very simply it does something which is comparable to the Monte Carlo. Okay, so I'm running a bit late, so perhaps now we take 10 minutes of break. But if you have questions, please ask them now, and the next part will deal with way to mix Monte Carlo and eligibility traces. We'll pause recording. Okay, so we are back. If any of you got a question, please ask. Otherwise, I want to do a quick recap. So I just want to stress basically three small things. The first is what we've done in all this algorithm here so far is that we have taken something which we know should be an evaluator of the value. For Monte Carlo, what we assume is the value is the return. So in a sense, our value is the expected return, complete return, discounted sum to infinity, and the algorithm so takes account of that and takes the return it sees and tries to average them out in order to evaluate the value. In the temporal difference, what is the return is the return which is called sometimes GT t plus 1, so which is the return given by this, the instantaneous reward plus gamma v. So again, what we are doing is we are trying to make our assumption, my evaluation of the value as close as possible to what I see as R plus gamma V. Okay, so in a sense, Monte Carlo takes the complete return and tries to average the complete return to get the value. The temporal difference takes the instantaneous reward plus gamma V, and that return, which is the one-step return, tries to assign it to the value. And then we see other things. But what I want to, so this is basic idea. Also, in the future, we will see that we will take some kind of evaluation of the return, and then we will try to assign to the value. What I wanted to stress here, which perhaps before I was not, I did not stress enough, is that this method, what does for this method to be model free? It means that they require only trajectories. Okay, so we have done this very simple random walk environment, very simple random policy, but this works. This small script I've shared with you works for any environment, any policy, as long as they are table action, table space. So here I have an environment random walk, and I have a policy which is half-half. Okay, but if I were to have an environment 2, which is a super secret spacecraft, NASA, Tesla, millions of euros, and the policy is some strange thing which requires millions of states, I don't care. As long as I have a list of states and a list of rewards, this very simple, very basic algorithm can produce a state value, okay? Because the model inside this algorithm R, the model does not appear anywhere except that for the size. So the learning algorithm must know how many states there are and trajectories. So what is really producing the trajectories for this algorithm is completely irrelevant. Okay, So we are doing the simplest random walk, random policy, just because we want to have a benchmark. But these very few lines are extremely general. Okay, I just wanted to stress this. Okay, so let's move on. I will do very quickly what I've just said before. So Monte Carlo, what they want to do is that they wait at the end of an episode so that they can evaluate the return, the complete return. Remember that the complete return is just defined as the reward, instantaneous reward plus gamma, the discounted reward, then the discounted reward afterwards, and etc. etc. Okay, and this the point of Monte Carlo algorithm is that they want to update the value using the complete return. One step temporal difference, also known TD0. Instead, they can update every step, but what they use is that they say, okay, we take care of the one step return, which is defined as the reward plus gamma, the value. And I'm going to update my value with using only the one step return. Okay. Now we can mix together the thing, and we can see that there is a whole class of methods which are called n-step temporal difference, which use the n-step return. The n-step is just something in between Monte Carlo and temporal difference. For example, let's say the n-step is gt t plus n, which means that the first n steps, it takes the experienced reward. So it's the reward, instantaneous reward, plus gamma discounted reward. Again, I apologize. Then it's gamma squared at t plus 2, plus all the discounted. But the last step, instead of using the experience, it uses information which it has. Okay. So clearly it's between the two. What does it mean? It means that there are a whole class of algorithms in which we update the value using essentially what we have as the n-step return. Okay, so as before, my new value is going to be my old value plus this learning rate, the return I just experienced, minus the value I had. Okay, so the entirety of these classes of algorithms essentially said, what is my approximate of the value? Can be the complete return, one-step return, n-step return. I don't care. My update is I have my old value, and I will add a small part of the difference between what I've just experienced, which could be a complete return, one-step return, and return, and my previously evaluation of the value. Okay, so this is very general. I will not even go into the code. You will find, because I mean, it was just to show you that there is a very simple way to care about Monte Carlo and one-step temporal to mix. Yes. So question about this. Now we go, unfortunately, in a part which is a bit more technical, but there is some mathematics, but a very simple message. So I hope that at least the message can be used, and mathematically you can discuss if you want. So why it's called temporal difference zero? Because it's actually one specific case of a whole class, which is called TD lambda, where lambda is the number between 0 and 1. We will see that lambda equals 0 brings back temporal difference 0, and lambda equal 1 brings back Monte Carlo. So temporal difference lambda is very elegant because actually allows us to bridge these two concepts of Monte Carlo and temporal difference. What it does, again, it defines a return, which is called the GT lambda, so the lambda return, which is something which includes all the returns we've seen so far. So the GT lambda takes GT plus 1, which is the one-step temporal difference return. So the return we have defined as the instantaneous reward plus a value for the next step. And it takes with weight 1 minus lambda, I don't care. But the next one, so the GT t plus 2, takes with a decaying factor lambda. The GT t plus 3 with a gamma squared, okay? So mixes all the returns we have defined so far into one single return, okay? So we can write it as the, sorry. Yes, I apologize. Since I have two notebooks, I have to correct both of them. Okay, so the definition of this return, which is called the lambda return, is just the summation of all the returns of 1 step, 2 step, 3 step, 4 step, 5 step, 6 step, etc., weighted with a decay factor lambda to n minus 1. Okay. Essentially, it means that let's say you can rewrite it as you want, if you wish, in two terms, since after termination, the return is just the complete return. So after termination, all those terms go back into one term, which is this. So you can, this infinite sum, you can split in the sum up to termination, which is the first sum, which is a sum in terms in which you mix experienced reward and value function at some point. Okay, so it's a mix of experience f and expected values, and a last term, which is just the the complete return. But this is just to show that if you split them like this, you can see that if you put lambda equals 0, then of course the second term dies, and all the terms with gamma, with lambda n more than 1 die, and only one term remains, and which is g dt t plus 1. So if lambda equals 0, the return is the one-step return. If lambda equals 1, the whole part here dies because 1 minus lambda goes 0, and this term here is remains just gt, which is the complete return. So lambda is a parameter which allows us to go from 0, which is one-step temporal difference, to 1, which is complete Monte Carlo. So why do we want something like that? Because we've seen that, or also you've seen it in the classes before, that temporal difference is very good because it bootstraps the information. So it does not require, it does not use only the experience you have in that moment, but it uses also the information you have accumulated before. Because it has, if you have a good notion of a value before, then you can use it in the one-step return. But on the other side, Monte Carlo has a very good, I mean, you cannot have wrong information. You can have wrong information of the value. If you, for example, if you start with a value or expectation very far from the correct one, every time you do one step temporal difference, that error will be brought into the definition. But if you do Monte Carlo, you do not require previous knowledge of anything. Everything is exactly as experienced. So it has no bias, okay? But so one has a very large variance, but has no bias. This is Monte Carlo. And the other one, the temporal difference, has a very low variance, but they can have a huge bias, and this is temporal difference. So having a way which switches between one and the other, which is TD lambda, is a very helpful way to mix the two. Indeed, it's known that the TD lambda with an intermediate value of lambda works better than the two parts. full Monte Carlo, full temporal difference 0. Okay, the problem is, as you can see, that as defined, you again require all steps. Okay, so temporal difference 0, you require only one step and you can do an update. But here you have one step update, one step return, two step return, three step return, four step return, and etc. So in this, we can see as a forward view. So the return at time t lambda is given by all the returns in the future, which is not useful because again, as Monte Carlo, you need to wait the whole episode and go back, which is a waste of time. Now, there is a way to deal with that, which deals with some way of retaining memory of your past visits, which it's called eligibility traces. Okay, so I want to split this next part into two parts. One is just hand waving, which is saying that what are eligibility traces? Eligibility traces are a way in which you store information about where you were and you assign updates to, instead of only the state you've just visited, to all states, but with a weight with changes upon how far ago you visit the state. Okay, so eligibility traces, in a sense, are a tool which we can think of as a empirical tool. Just, I don't want to change only a state, but if I have, let's say I have experienced a state 0 and then I experience state 1, I do not want to change only state 1. I want to change also state 0 because, I mean, it was just before me. So whatever, if I now find the state 1 is very good, then also state 0 should be very good because I just experienced it. And in this way, we just want to see the eligibility traces as a tool of having memory of the past and changing all states with some memory of the past. And this can be a message which is independent by what I'm showing now. Now, what I want to show now is that in the basic form, eligibility traces are a way to compute lambda return, which are returns in the future, without having to wait for the end of an episode. Okay. So keep in mind these two things. I have a way to combine Monte Carlo and temporal difference 0, which is called temporal difference lambda, which uses lambda returns, which in principle are something which have to be computed in the future. There is a way, which is called eligibility traces, to do it at each step instead of at the end of an episode. This tool, which is eligibility traces, is also used in general as a tool to have a memory of where you have just been, and this helps to increase the efficiency a lot. I hope I'm not completely lost to you now. I will try to do the mathematics, and then we will hopefully see what I mean. Okay, so we have said that TD lambda aims to do this update here. I want to change my value with a small alpha so that my value is as close as possible to the reward return GT lambda. Okay, and then now let's expand GT lambda. So GT lambda, by definition, is equal to 1 minus lambda, the first one step GT, so instantaneous reward plus gamma V, this is return one step, plus lambda, two-step return, which is real R, real reward, plus gamma R, plus gamma squared, the value. Then it's the three-step, which it has the weight gamma squared, and it has the reward plus the reward plus gamma squared, the other reward, plus value. And again and again, okay, so he has all the terms, all of these have some lambda to some power, and have many actual reward plus gamma to some power, the value. Okay, this is if I expand the return. Now, you can see that here something happens in the, let's see if I can do, okay. You can see now that something happens in these columns here. Okay. Actually, these columns here are, something appears over and over. So for example, the reward of time t plus 1 appears all the times. So you just can sum up all of them. And in particular, you have to sum up, and all of them have a weight 1 minus gamma, and then you have 1 minus lambda, lambda 2, 0, lambda 1, lambda squared, etc., etc. So all of this here sum up. Sum up, and you, since the sum of infinite lambda to the n is equal to 1 minus lambda, all of this term with containing r to time t plus 1 sum up exactly to r t plus 1. So all the factors cancel out. Okay. The one with r t plus 2 are exactly the same, but they have one additional gamma and one additional lambda. So they are sum up to gamma lambda rt plus 2. Again, those with rt plus 3 sum up to gamma lambda 2 squared rt plus 3. All with rt plus 4 sum up to gamma lambda to the 3, etc., etc. Okay, and then the value, you can see that the value actually appears only once. With two terms, 1 gamma vt minus lambda gamma vt. Okay, so actually all of this strange thing here can be rewritten into this sum here. Okay, it's exactly as before. I just said that all the terms are sum up to just this. All the terms are t plus 2 sum up to this. And then I took the value, which had only one term, gamma lambda gamma n minus 1 and minus lambda gamma to the n, and I just written like this. And now you can see that actually this term here corresponds to something very, very similar to my delta. Okay. This is the reward plus gamma v minus v when you have only one passage of state. This is state t plus 1, t plus 2, and I have the reward. Okay. So I can use this in the sense that if I want to do a change at time t, it's like I'm keeping on doing an update to this state here. So the value of state t, it's like I do it with weight 1, I'm doing it at t equal t. At the next step, I'm again updating the same state, even if I'm now in another state, I'm updating the same value of the same state, but with a decaying factor. Okay, it's like at time t, I'm in a state and I have memory of being there. Then I move away, but I have a memory which decays with time of being there. Okay, because at time t plus 1, I'm somewhere else, but I'm still trying to change the value at the state t with a decaying factor. Then at time t plus 2, I'm in even other place as t plus 2, but I remember that I was there 2 times ago, and so I will still increment that value there, but with even smaller terms. And then I will move again, but I will still try to update that value there. Okay. Now, there are some subtleties all around, but the point is that eligibility traces, as a general rule, keep track of where you've been in the past and change the value, update the value of where you've been in the past with what is the current estimator delta. Okay, so you are somewhere you calculate what is the delta because I was here and I did this action, I got a reward, and this is my new value. So this is delta, which usually, this delta here usually enters in the calculation of only the value of st plus 2, but instead we use the same delta, which normally is being used only for st plus 2, also for st, but with a very small factor. Okay. Eligibility traces in their most extremely simple way are just some weights, which are weight for all of my states, which at the beginning are 0. Then if I go into a state, I get +1. And if I move away from the state, I just get a multiplication lambda gamma. Okay, so I have weights everywhere, which are 0. Then I visit a place, it goes to 1, and then it goes down. And I visit again, it goes +1, and then it goes down. And at each step, instead of updating the value only for the state I am in, I updated the value everywhere with weight proportional to the eligibility traces. Okay. So what I wanted to say is that all we've done so far, essentially, the instantaneous reward and the standard return were used to update the value of a single state. So if at t equals 3, I was in 3, all my different evaluation of the return were used to update the value of state 3, but with the eligibility traces, at time t equals 3, I am in state 3, but all the values everywhere get updated, but some more and some less, depending on how long ago I was there. Okay, so it's an extremely helpful tool because it connects past experience to present experience in a way which none other can do. Okay, this was why I was saying that there is a connection between eligibility traces seen as memory and eligibility traces seen as a way to implement TD lambda. Okay, I hope this was a bit clearer. The nice thing, because right up to now it seemed that it was a mess from the point of view of mathematics. The nice thing is it's extremely simple to implement eligibility traces, at least in this very simple way. This is the pseudocode, which is essentially the same as before. So we initialize values arbitrarily. We initialize eligibility trace to 0 because we have not visited anything yet. We start with an episode. I take an action. I do the action. I observe the reward. I observe the new state. I'm doing the usual time different 0 delta, which is r plus gamma v minus v. And then in that state, since I've been in that state got eligibility trace +1. And then for all the states, not the state I mean, for all the states, I do an update which is proportional to the learning rate and the eligibility trace in that space there. And then all eligibility trace for all spaces get multiplied and decay with the factor gamma lambda. And then I'm in a new place and I take another action. I collect a new reward, I collect a new state, and I do the same. The eligibility trace in the new state got +1, but then all the states everywhere get updated with this simple rule. Okay? There are many subtleties. So backward and forward expression, as I define here, are perfectly equivalent only if at each time I were to use the value as defined in the past, which is not true. So you see that now I was saying that at t +2, this is the delta. This is not actually the delta, because the delta is actually using the value of v as defined in T+2. Okay, so these two are not perfectly equivalent if I do a one step-by-step update. But most of what I said is true, and the general gist of eligibility traces is there. Okay. Do you have a question about this? I know this is a bit tricky, but I hope that the main message of memory is there. Do you have questions? You have too many questions and you don't want to start. Okay. What is the nice thing? As I said, the nice thing is look at the code. The code, the only thing that's different from before is that I need an eligibility trace, eligibility factor, decaying, a number, again, between 0 and 1. And I need to just store a new vector, which has the same size as the observation state. That's it. Then, what is the single step update? Is the same as before because I have to create a delta, and I just need to do this very simple operation on the eligibility traces. Either the eligibility traces get +1 and then decay, or they just decay. Okay. So you can think about them 2 seconds, but essentially what we've said and what we will see now is that you have to update the eligibility traces because I just visited the state. So one of those eligibility states will get +1. Then I define the delta as exactly as in temporal difference 0. And then instead of updating only one state, I'm updating all of the state with eligibility traces. And then I decay all of the eligibility traces. Okay. So in a sense, if you want, here I have step 3, which is apply update to all state proportional to eligibility traces. And then I have a false. Okay. Indeed, let me go. If I were to write it now, I'm clearly a mess. Yes. This is, I mean, as always, they are super simple. I update the eligibility trace for the current visited state, self eligibility trace in the state S +1. I define lambda as before, and I take care that at the end of the episode, I don't have a value for the new state. Then apply the update, which is proportional to delta, is proportional to the learning rate, but is proportional to the eligibility trace everywhere, because now this is a vector of values and this is a vector of eligibility trace. And then last thing I do, I apply the decay factor, and if the episode is finished, then all the eligibility traces go back to 0. Okay. Again, what are in general eligibility traces? We have seen them like come up from this TD lambda return. So this return which mixes all the 1-step, 2-step, 3-step returns. But actually, they can just be seen, and they are generally used in many forms as the memory of a past system. So I go through my trajectory, and it's like I'm lighting up some memory of where I am, and then the update, instead of being only localized on where the current system is located, is spread to all the places which have been recently visited. Okay, so the main difference is that in Monte Carlo on time difference 0, if I am in ST at time t, only the value relative to that position is modified. Okay, and it's modified in Monte Carlo for the complete return, in TD0 by the one-step return or n-step return, it doesn't matter. Only that value there is modified. But with eligibility traces, the return approximation, which again, one-step return, complete return, I don't care, modify all states with some weight. Okay. It's called eligibility because, in a sense, those are the states which are eligible to change. So we will see that you will see the function approximation. You will not be in one state. You will be in approximation of the state. So all the states which share some feature will be changed accordingly. Okay. Then essentially we can see what is the last thing is just let's do again. We take a learning rate, we take a lambda, we know what is the optimal value, we calculate the empirical error, we create a random walk, we do some average runs, and we do some number of episodes, and we see what is the average performance of the T lambda. And you can, yeah, I did not define it. Okay, one day I will learn, but not today. For example, you can see the TD lambda, okay, now the learning rate was very small. Let's say the learning rate which is larger. This is very, very large, so it will learn even faster. Let's take I mean, now, essentially, I introduced a new hyperparameter which I can change, but essentially this is a way to bridge temporal difference in Monte Carlo. Just one picture to show all the difference. Between, remember that TD1 is just Monte Carlo. What happens? Let's take just one episode. Okay, what is the change to the value of all states at the end of one episode? So I starting with all the value equals 0. I'm running up to the end of an episode, and I will try to see what are the changes which the 3 different algorithms do to the values for the same thing. So I have the same environment, a random walk. They all experience the same trajectory. But now I want to see at the end of the first episode, what is the change, what is the actual value they predicted starting from 0. And I will put just 0.1 as learning rate for all of 3, gamma equal 1. Okay, and I do size equal 10. Okay, size equal 5, the same as this one. And I'm using, so lambda equals 0.8, lambda 0, which is TD 0, and I'm using Monte Carlo. And actually, you see why TD lambda is very nice, because actually all recently, all algorithms that I created before can be written as a TD lambda. So in a sense, I could have started from the end and finished in 10 minutes. It would have been even less nice as a lecture, I'm afraid, but it could have been done. Okay, so you see that after one episode, nothing changed. Can you guess why? Yes, I cannot hear you, but I know that you wanted to say something. Please unmute. I'm sure you have the correct answer. Kiran, is it right? No? Anyone wants to guess? After one episode, all the values stayed 0. Remember what is the environment. The environment is a random walk which has 2 ways of termination. Either it terminates on the right and gets +1, or it terminates on the left and gets 0. So by chance, the system just terminated on the left, so we had 0 signal essentially. So it has 0 reward, 0 everything. So this is just one episode can happen which there is no update. But let's do another episode which nothing happens. Okay. So now I have 3 curves, and let me give me 1 second. I apologize. I thought I had done this before, so that we can see which one is which. Apologize for this. Okay. Now we see the 3 curves. Evidently, clearly, the single episode finished with a 1. So it finished with a positive reward. And then I have 3 types of updates, which are rather different. So one is the temporal difference 0. Why is it like this? There is a simple reason. This temporal difference 0 can see only 1 step, and then it uses the previous node information. So until it has a reward, the information is always 0. Only 1 step sees a signal. It's the last step in which I get a reward +1. So it says, okay, this state here, I saw a reward +1. So I'm upping the information, but it ups the information only in that particular region there. So it goes up by learning factor, but all the other steps contributed to nothing. Then Monte Carlo, what it says that you have to keep the return for all states. So all the returns, since this is gamma equal 1, all the returns just sum all the reward up to now. So all the rewards are equal to 1, which is the only reward it took. So all the returns, I apologize, are equal to 1. So I'm just adding 1 multiplied by learning factor, multiplied by all the times that I've been in a state. Since this is a random walk, I've been mostly around the center, and then I exited. So you can see that the prediction, since I'm adding using the return, which is 1 for all of them, the prediction is that actually the value is larger in the middle, because I visited many times the center region. But TD lambda, remember, it has a decaying memory. So the largest change is in the state which has been last seen. And indeed, it already shows the shape which it should be, because the shape, you remember, is just 1/6, 2/6, 3/6, 4/6, 6. So the shape should be linear. So time difference is weighted down by the fact that its previous bias was total 0, and only one state changed. Monte Carlo has many changes, but they are wild. Wild because it has a very large variance. But TD lambda has a memory, and so it combines the efficiency of both. It has a good estimate at the end, say, okay, this is where I got truly a reward, and it propagates back to all the states visited previously, but with a decaying factor. So this basically are the 3 differences between the 3 algorithms. And this concludes the lecture. I hope that some of it was more clear than some other parts. And if you have, so I will provide the completed code with, it is also a few correction of typos, etc. You will get this, so don't worry. You can go over it. I also pointed out sometimes I found, for example, for the eligibility trace for the backward and forward, I found that this blog, which is a part of the Sutton and Barto online material. I think it's very clear if you want to see it more. I've tried to be, so this random walk is the exercise 6.2 of the book. So again, there you can see that there is some material. I apologize that one thing which I did not do is that I did not follow the convention using the lectures and Sutton Martin. So in the convention, the reward has a time incremented by 1. I use the convention where the reward has not time incremented by 1. So please be careful of, for example, this here. It's consistent with my notation, but my notation is, I mean, I just do it for convention, but actually, if you see it in your lecture, should be RT plus 1. Okay, but it's just convention, but just please take care of this, then take note of this. And I try to put as many comments as possible so that these algorithms are simple. I want to, but they are simple by their nature. This I want to assure you. And if you have questions, if you want to expand on them, then you can also write to me on Slack. Let's stop